Lecture 16 covers sections 6.1 through 6.1.4. At the end of this lecture, you should be able to determine the average normal stress, sigma average, and average shear stress, tau average, generated within an axially loaded member and where the maxima of these stresses occur. You should also be able to determine if an axially loaded member is in compression or tension, determine the bearing stress within an axially loaded member, and determine the shearing stress, tau sub ing, within components experiencing single shear, double shear, and so on. This will be applied later to the allowable stress design model. We want to determine the effect of the external and internal reactionary forces acting on individual components, namely the material's behavior. Internal forces or stresses lead to deformation, which in turn leads to movement, wear, and potentially failure. After we determine the amount of stress an object is subjected to, we can determine the proper size and material for a component such that it can withstand the applied forces and function as intended. Axial loading occurs when a member is subjected to a system of two or more collinear forces that act along the axis of the member. For example, we can have F1 and F2 pushing inward on a rod. If we figuratively cut this rod anywhere along its length, we can see the internal reactionary force R develops to counteract the externally applied force and maintain equilibrium. That is, if we cut the rod in the middle, we'd see R opposing F1 and R opposing F2. These reactionary forces can either resist a member being compressed or it can resist a member being stretched. Compressive forces tend to decrease the length of a member, while tensile forces tend to increase the length of a member. As a result of internal reactionary forces, stress is generated within the member. The average normal stress, sigma average, is a measure of the intensity of the internal reactionary forces and is equal to R per A, with units of pascals. In this instance, R is assumed to be a uniform distributed load normal to the cross-sectional area. Conventionally, a negative value for average normal stress indicates that the member is under compression, and a positive value indicates the member is under tension. For example, let's say we have a balsa wood member with geometry shown below, and we want to determine the average normal stress existing within the member. We'll start by making an imaginary cut in the balsa member and label the internal reactionary forces R. Note that R is defined as existing along the unit normal vector of the cut surface in the opposing direction of the applied force. We can now apply equilibrium equations for a free body diagram of either cut member. Since the summation of the forces in the x direction is equal to 0, we find that R is equal to 500 newtons. We can now insert this value into the equation for average normal stress. Sigma average is equal to R per A, where the internal reactionary force R is 500 newtons, and the area it's acting on is equal to 90.7 millimeters squared, or 90.7 e to the minus 6 meters squared. Dividing this gives an average normal stress of 5.51 megapascals. Since this value is positive, we note that the member is in tension.